The title of this talk is Generating Hardware, Click to NetFPGA Toolchain Using LLVM. And I'm just curious, right now, how many people in this audience understand what that title means? Okay, a few people. Okay, good. So this is kind of the outline of my talk. I'll give a brief motivation, some background about some stuff that's not too closely related. A lot of this is not very closely related to LLVM, so it might be a little bit unfamiliar. And I'll proceed from there. Some terminology, high-level synthesis. If any of you were here for a previous talk, c2verilog.com discussed this. Basically is the concept of taking a high-level program and creating hardware out of it. So it's abbreviated HLS. So one of the goals of this project was to study the applicability of high-level synthesis to packet networking, and to have a tool chain that would be able to take Click, and I'll explain more about what Click is, to NetFPGA, and I'll also explain what that is. So Click is a software platform for building packet processing systems by Eddie Kohler. It runs on Linux. It's a software architecture. The basic idea is that you have packet processing elements which will take in a packet, perform some kind of small operation on that packet, and pass it on to some other element. And by composing these elements in different ways in a graph, you can define the functionality of a router or some other packet processing system. So it's very popular because it's fairly easy to experiment, to try out new ideas fairly easily. There's there's a fairly large library of existing packet processing elements. And along with this framework, there's a configuration language which is used to basically instantiate these elements and interconnect them and customize them. Down here in the bottom of this slide, there's a kind of a small example excerpt of such a packet processing graph of each of these boxes as an element, and it performs some function. So this is a software platform. Now the target of this project is called the NetFPGA. It's a device that was developed at Stanford. It's basically a PCI card with 4 gigabit Ethernet interfaces with an FPGA on board. So this is kind of a platform for research and teaching for line rate packet processing. It's fairly popular among academics in the networking field. And there's several open source Verilog designs. Now, one of the difficulties with using something like this is there's kind of a learning curve. A lot of people in the academic networking community aren't necessarily hardware experts. So one of the goals of this project was to make it easier to program one of these things. High-level synthesis I briefly described earlier. So you take a high-level program and produce a hardware description. Typically, it's referring to some C or C++-like language, and targets a low-level language like Verilog or VHDL. Now, there are a lot of caveats, a lot of limitations in these languages, and a mapping from software to hardware is non-trivial. And so for people who have this high-level picture of, okay, I can take a C program and I can make hardware out of it, it's not quite that simple. Typically, it's fairly limited, the functionality, and you have to keep in mind what the hardware is going to be like when you write your program. Only subsets of the languages are supported. Several of them introduce some complications. Dynamic memory allocation, function pointers, recursion, some examples. So you simply can't take some existing code base and feed it to this tool and have it work. And again, one of the goals of this was to somehow make it work. Another aspect of these tools is by far the majority of them are closed source commercial products. There are some exceptions to that. This is a tool that was used in this project called AHIR. Stands for a Hardware Intermediate Representation. And it's kind of a midway point between a software-like representation like LLVM and a hardware representation which knows about things like logic gates, registers, and so forth. You basically have a conceptual separation of control data and storage. So the control is modeled at PetriNet. So it's similar in many ways to your typical control flow graph. And basically, you start with an LLVM IR, convert it to this AHIR representation, and from there you can generate VHDL out of it. So that's kind of the way the tool chain goes. So each function will be mapped into a VHDL module in this framework. There are some limitations as well to this tool. Like other tools, there's no recursion or function pointers. So this is an issue with something like Click, which has virtual function calls. And there are some things that will be done to deal with that. There's also, along with this, a built-in library for asynchronous communication between modules. And that's actually important for parallelism purposes. So here's an example kind of showing you what the control and the data portions of this AHIR model. Basically, you have the C code D equals M plus N. And this is fairly trivial. You only have one operation. You have the data path here, which consists of an adder. On the left side, you have a control and data flow graph merged together. And you can discern between the two by the line. Control edge is a solid line, data edge is a dotted line. Here's a more complex example. You have this C code excerpt here. And when you compile to LLVM, you'd have an SSA version of that. And from there, that gets converted into this, this representation here, which is depicted graphically here. And that graph shows both the control and the data flow. Here's a picture of the same thing, but now with the control path and the data path separated. In the control path, you'll notice that, well, I guess I'll back up a little bit to explain some of these letters. The diamonds in the middle, the F is a fork, the J is a join, the B is a branch, and M is a merge. So here on the control path, it kind of branches out here at the top, and there you execute in parallel, both branches. On the second part, you choose one. And the data path and the control path are linked by signals, by wires, that allow them to communicate. For example, the control path will need to indicate to the data path which value of D is going to be assigned, whether it's D0 or D1. Likewise, the data path needs to communicate to the control path the results of a test. Okay, so that was some background on Click, NetFPGA, high-level synthesis, and AHIR. Now I'll talk about how we kind of take all these things and put them together into a tool chain. So first I'll discuss kind of one issue. In software click, it's a fairly large code base, and when you compile it, you have all these elements in your library that get linked in. And this isn't a problem in software. This is fairly cheap, you know. However, it's really too much. It's a lot more than you need. In the case of click, you have a particular configuration that you're interested in, and you process packets with that configuration. So when you're generating hardware, really you want to cut out all the unnecessary things and include only what you need. And a lot of this code is initialization code, configuration parsing code, which you really don't want to run in your hardware. But in your hardware implementation, what you really want is an actual chunk of hardware for each element instance that actually gets created. But when you run it in software, you have to go through the initialization process before you know what those instances will be. It is possible, and they do manage to cut out all the unnecessary things and include only the things that they actually use for a particular configuration. And the reason they're able to do this is because you have an initialization phase followed by a packet processing phase. So another thing that needs to be addressed in this process is the removal of virtual function calls, for example. And these can be resolved to static function calls. And also, after generating the hardware, you need to be able to hook it into some kind of environment. So here's kind of a description of the various steps involved in this process. First, you start with your clicks C++ source code, transform that into a hardware-friendly intermediate LLVM IR, and from there go to here in VHDL. The click library did have to go through some changes. It's basically porting it to a new target. Instead of Linux, now it's porting to FPGA target. One example of something that needed to be changed was the memory allocation. And when I describe the environment that it gets integrated into, it'll become clear how that takes place. So that's a modification of the click library. The tool that customizes and eliminates unnecessary code is called click2LLVM. So basically, the approach is to use the click library itself to run the initialization phase of the router, to process the configuration. And once you've set up the click router data structure, you basically freeze that and dump it as memory in LLVM IR, but dump it as constants. And that'll be used later. And then also, you'll need to use the hardware target library to produce hardware-friendly versions of all those elements. And after that, you'll have aggressive optimization phase, which cuts out a lot of the code. And once that's been achieved, we can feed that into here. Here's kind of a graph of the workflow to help visualize how everything fits together. So at the top corner, you have the source code that you can download from, download for free. It's open source and unmodified. And you have basically two versions of the header files, one for running on Linux and one for running on the NetFPGA. You compile both of those through LLVM G++. And on the top side, you produce LLVM IR files that are hardware friendly for the hardware target. And the bottom, you use that to run this click to LLVM tool, which will dump the router memory as constants. And that takes in the configuration file, which specifies the actual router that you're going to build. Then you go through, you link them together. You go through some aggressive constant propagation and dead code elimination. They come up with an optimized intermediate representation and feed it in through the tool chain. And at the end, you hook it into a wrapper, which defines the hardware environment that it'll operate in. This is what the hardware wrapper looks like, implemented in VHDL. So the generated hardware goes in the middle, which consists of the various packet processing elements that are connected together. The queues it's basically a queue of pointers, which is how the memory subsystem is managed, how memory space is allocated. The input module interfaces with NetFPGA hardware environment, which feeds in packets a word at a time, and that writes it down into a memory subsystem, which is then accessed by the generated hardware. And the queue at the top is the free queue, which keeps track of free locations. And the output module transmits the packets on the back side. So this kind of goes along with the click way of passing packets between modules, which is to pass the pointers only, and the packets themselves stay in the same memory location. This is different from what the NetFPGA reference designs do. And the click elements that are generated can create or destroy packets, as is allowed in the source code. And that's why it has direct access to the free queue. So here's an example. Here's a configuration written in the click configuration language. There's only 3 elements in this design. It's very simplistic. You have a source, which hooks into the FPGA to generate packets. You have a destination where you'll transmit the packets, and you have a module which modifies them. This is a standard click module from the click distribution called EtherMirror. And basically all it does is it swaps the Ethernet addresses of the packets. And so this feeds into the tool chain. This is the original C++ definition of the code, unmodified. This module has implements a function called simple action. It is a virtual function that any element with a single input and a single output can implement, and just performs a modification of the packet and passes it on. There's this notion in click of push and pull, and that reflects the flow of execution through the click program. Push will call the downstream element, a virtual function call to the downstream element, and pass it a pointer. Pull will call the upstream element, and simple action can do either push or pull. Here's an example of kind of what level of optimization and dead code elimination you can get through this toolchain with this simple configuration. The output of the unoptimized output is over 16,000 lines. And after constant propagation and so forth, that brings it down to 171 lines of actual useful code. There are some transformations that take place for the purposes of integrating it into a here and making hardware out of it. The toolchain creates a function per click element with this name, ahir glue element name. The click library calls, as I described before, are modified for this particular toolchain. Instead of calling push or pull on your downstream or upstream element, you actually use an ahir library function to read or write from a FIFO. So you have FIFOs that go in between elements. And the reason this is done is to enable all the elements in your design to operate in parallel simultaneously. And this example here, you can also kill a packet, and the kill function is implemented as writing to the free queue, that pointer, instead of passing it on. Here's kind of a very busy slide that shows an excerpt from the optimized LLVM IR. I've kind of highlighted in red the more interesting parts, the name of the function, and you have the other two parts, which are the library, the ahir library functions that I described that read and write to these FIFOs. So this is the VHDL code that's produced. It's relatively few lines of code to implement this functionality. And this is an excerpt in case any of you know VHDL. It's basically a definition of the top-level pins of the data path. And the parts that are highlighted in red are the pointers, the packet pointers that get passed in and out of this element. So this is a pretty early prototype. It's really been working through some simple examples, simulating. It hasn't even really been prototyped in the FPGA itself yet. It was about 2,000 lines of new code, 200 lines modifications to the click library. And there are some, it works for simple click configurations, nothing too fancy yet. And this is kind of description of the future work that they plan to take this with. And that is the summary. And that's the end of my presentation.